Hi, this is Google Kickstart question, magical well of lilies. So we have a well that contains L number of lilies, and we have a basket that is empty at the beginning, and we need to move all the lilies from the well to the basket. We can use one of these three actions at any point. The first one is we can toss one coin to the well, and by doing this we can get one lily from the well to the basket. Or we can toss four coins into the well, and by doing this we will update the memory with total number of lilies collected so far. So if we have a memory, and if the number of lilies collected in the basket so far is equal to x, so if we toss four coins into the well, we update the memory with the value of x, which is the total number of lilies collected so far. The other option we can do is toss two coins into the well, and by doing this we add memory value to the basket. So if we have x here, we toss two coins, we can move x number of lilies from the well to the basket. And the question is, we need to move all these lilies from the well into the basket using the minimum number of coins. You can solve this using trivial solution, which is at the beginning you have 0 lilies at the basket, and you spent 0 coins, and you can do one of the three possibilities: either spend 1 coin or 2 coin or 4 coins. And by doing this you will update the value of how many lilies collected so far, and also the number of coins consumed to reach to these steps, and also the same for 2 and the 4. Then we continue doing this, the same procedure. We can spend 1 coin, 2 coin, 4 coins. Then we update the value for L, the number of lilies collected, and how many coins we spent. We do this for everything. We do the same 3 possibility at any step. At the end we can arrive to, or we can reach to L number of lilies at any branch here, and it has the number of coins. So we will get our solution by calculating the minimum among all of these answers. This is expensive solution because the time complexity for this is exponential, and we need to find a better solution. And for this we will use dynamic programming. So here we have a table, and this table is of size L plus 1, and the target is at any index we need to calculate the minimum number of coins required. So here, for example, at 4 we need to calculate, or it will store the minimum number of coins required to collect 4 lilies. At 9 we need to calculate the minimum number of coins required to move 9 lilies from the well to the basket. At L also it will store the minimum number of coins required to have the L lilies, and this will be our final answer. All the entries at the beginning contains the values integer max, and now we start at value 1. We need, so we ignore 0, we start at 1. What is the minimum number of coins that we need to get 1 lily? The answer is 1. You cannot spend, based on these actions, you cannot spend less than 1 coins to get 1 lily, and this will be our starting point, and then we will iterate from this one to L, and at every iteration we need to do one of the following 2 actions. We can spend 1 coins at any point and update the value next to it. So at 4 we will update the value at 5, and the formula will be TB of I plus 1 equal minimum of the value stored of at I plus 1 VS1 plus TB of I. So this is because we spent 1 coin, so 1 plus the value at stored at I, and we compare the minimum and we update this value in I plus 1. So this is the first action we can do. The second action is we can spend 4 coins, and to update spending 4 coins will update the memory. So at any index, let's assume we are at index 3 here. So we will spend 4 coins, then we will spend 2 coins to get 3 lilies, because we are at 3. So 3 lilies plus 3, because we spent 2 coins, equals 6, and we will update the value at 6. Then we can also spend another 2 coins and update the value at 9. Can spend another 2 coins and update the value at 12, then 15 up to L. So TB, the formula for this will be TB of I plus I plus I equal minimum of TB of I plus I, and here we spend 4 plus 2 plus TB of I, and this is for the first jump, and we need to keep doing this for so TB of I plus I plus I. This is the second jump, equal minimum of TB of I plus I, and 4 plus, now we spend not only 2, we spend 2 plus 2 plus TB of I, and we keep doing these jumps until we arrive L. And notice this is we can do this in a for loop for these jumps. Let's look at the code implementation. So here we parse the test case, and we need to solve for every test case. this is our table. As we said, it's L plus 1 entries, and each entry has int max value, and this is so TB of 1 equal 1 coin, and we will loop from 1 up to the L. And this is our first step here, this one, for spending 1 coin. So TB of I plus 1 equal minimum of TB I plus 1, or 1 plus TB of I. So by spending 1 coin you get 1 lil, and we update the value at I plus 1. Or we need to spend 4 coins and do the jumps, so we keep looping until we arrive L. And so here TB of K multiplied by I, in this case is 2. So as we saw here, the first one is TB of I plus I, which is 2I, 2 multiplied by I. So our initial value is K equal 2. And here we need to check, first of all, it's within the boundary. So TB of K multiplied by I equal minimum of TB of K multiplied by I. And here we spent 4 coins for updating the memory, and we spent 2 coins multiplied by the number of jumps, and we update the number of jumps. And at the end we return the last element in the table. This will be our final answer.